All right, today I'm going to be talking about ZeroTrace, Oblivious memory primitives from Intel SGX. This is joint work with my supervisor, Sergey Gorbanov, and our collaborator, Christopher Fletcher from UIUC. So to motivate the need for ZeroTrace, let me start with discussing this problem of secure remote computations. So consider the situation where a user, Alice, has a program P and some data D and wishes to compute P of D. Now, she might not typically have enough computational resources to perform this locally. So what the normal solution is to use infrastructure provided by a cloud service provider. And as always, these cloud service providers are not meant to be trusted. And ideally, she wants three properties from this particular computation, which are confidentiality, integrity, and efficiency. So what is the dream solution for this problem? Imagine if there was some way for Alice to encrypt this data D under a secret key and somehow magically enable the server to compute all of this encrypted result P of D from P and encrypted data D. In fact, this dream solution sounds exactly like fully homomorphic encryption. So let's take a closer look at what other solutions we know for this problem. Broadly, there are two categories of solutions for this problem. The first being software solutions, such as fully homomorphic encryption. FHE can give you strong confidentiality properties, but it does not innately give you integrity guarantees. And in order to get that, you need to imbue it with a homomorphic signature scheme or snarks to get that. But more fundamentally, it's constrained by the fact that it has poor practical efficiency and lack of generality. While it can compute few families of functions efficiently, it's not practically deployable today for generic remote computations. And it's unlikely to change in the near future because of the underlying math. So we look towards other solutions. And another one is ORAM or Oblivious RAM, which can even give you similar guarantees. But ORAM can even give you better integrative guarantees than FHE. But the same problem of efficiency plagues ORAMs as well, and it hence has not been widely deployed in practice. There have been attempts to solve this problem from a hardware or architectural standpoint as well. One such solution is Intel TPM plus TXT, which is the Trusted Platform Module plus Trusted Execution Technologies. So TPM TXT too has been plagued with confidentiality attacks in the past, and hence is not really a solution that's acceptable today. In fact, it also has problems in terms of hardware isolations, and that it gives you low hardware parallelisms. But there's a more recent solution, as we've heard today quite a bit, which is Intel SGX. And Intel SGX claims to have solved this problem and solved all three properties for this problem, in fact. But this, however, was short-lived because over the last 3 years, we've seen from security research that Intel SGX is, in fact, susceptible to several side channel attacks. So our question or challenge was, can we actually design a system that meets the desired properties for secure remote computation? And in fact, that's exactly what ZeroTrace or Oblivious Memory Controller does. At a high level, the approach is to merge the privacy and integrity properties from ORAM with the efficiencies from SGX. So this is the outline for today's talk. I already spoke about the problems of secure remote computations and skim the shortcomings of current solutions. Now I'll discuss some of the preliminaries required to address ZeroTrace itself. And finally, we'll discuss ZeroTrace's architecture and also see some of the performance numbers that it has. So the first thing that we need to discuss is the background for Intel SGX. Intel 7th generation processors, Skylake and onwards, support Intel SGX. And in a single line, SGX is a set of new instructions for the x86 architecture that enables secure code isolation within virtual containers. And in order to achieve this, these processors are at manufacture time fused with cryptographic keys. These keys enable the processor to set aside a subset of DRAM called as PRM, or processor reserved memory, at boot time. Hence, in SGX, security is in fact bootstrapped from an underlying trusted processor. Access to this processor reserved memory is vetted through hardware mechanisms by the CPU, preventing the access of PRM by adversaries. Additionally, all pages of PRM at all times are encrypted with the CPU fused keys and also integrity verified by maintaining a Merkle tree of it on the chip itself. So SGX enables instantiations of secure virtual containers called as enclaves, which reside in this PRM and hence attain all the confidentiality and integrity properties that this PRM has. The threat model outlined by Intel SGX is that you can in fact compute securely via enclaves as long as this processor isn't physically broken into. And what this implies is that you can get security as long as no adversary can peek into the physical contents of the registers of this processor. In fact, if you want to learn more about this SGX architecture, I recommend Intel SGX Explained by Victor Kostan and Srini from MIT, or alternatively, Intel's patronizing learning resource, SGX for Dummies. So let's actually take a look at what secure remote computation looks like with Intel SGX. Alice, who has a program P and data D, can now encrypt this data under a private key and share it with this program P instantiated in a secure enclave, thus enabling P to compute on this data by decrypting it with the shared key. This data remains confidential with respect to an adversarial server, as it's always encrypted under these keys owned by the trusted processor, the blue ones in the figure. And this is what happens to all data encoded in this PRM. Code initialized in enclave can get integrated guarantees via what are called as enclave measurements, which are in effect SHA-256 hashes of the enclave initialization code and data. It's also efficient since enclave initialized programs execute with similar performances as native code. But as mentioned before, Intel SGX is susceptible to confidentiality attacks by software side channel attacks. So what actually happens here is, even though SGX prevents an adversary from directly inspecting or tampering with the contents of this PRM, it doesn't protect against these side channel attacks. And these side channels arise from the fact that in SGX, you share hardware resources with untrusted applications. Over the last 2 years, we've seen several academic papers that attack SGX enclaves and extract these sensitive data from these enclaves. Broadly, these side channels can be classified as page fault attacks, branch shadowing attack, cache attacks, and data access pattern attacks. In the interest of time, I'm not going to get into each of these attacks, but I'll actually refer you to the full paper where we discuss more about these attacks itself. Moreover, or rather additionally, SGX is also plagued with other functional limitations. Currently, this PRM is upper bounded to 90 megabytes, and exceeding this results in expensive paging overheads. Enclave codes are architecturally limited from performing I/O or syscalls. Executing code within an enclave mode results in what's called an enclave mode. And switching between this enclave mode and regular is a very expensive process because enclaves have to do what's called as an asynchronous enclave exit. And in short, what an asynchronous enclave exit is, before an enclave mode has to hand off this processor to untrusted code, it has to in fact clear the internal states of the registers so that an untrusted application can't see what the register contents are. So now we've covered Intel SGX, and the other preliminary left is ORAM or Oblivious RAM. So Oblivious RAM is the cryptographic primitive which was introduced by Oded Goldreich and Raphael Ostrowski in '96 to hide memory access patterns of a program. And in short, the very fundamental idea of an ORAM scheme is to access multiple data locations for each data request, and such that an adversary who views the access pattern traces cannot infer what was the underlying data request to start with. And this indeed is an expensive protocol, as shown by Goldreich and Ostrowski's seminal work, where they showed that you have to have a lower bound of at least logarithmic overhead in order to get Oblivious RAMs. And fundamentally, all ORAM schemes require an underlying probabilistic encryption schema, and we'll see soon why that's required. In our work, we make use of two particular ORAM schemes, path ORAM and circuit ORAM, which are both tree-based ORAM schemes. So over the next few slides, I'll actually try and capture tree-based ORAM schemes as succinctly as I can. In an ORAM setting, we consider data sets to be made out of blocks, where each block consists of an identifier, a leaf label, and the data itself. Considering a data set of n blocks, on the server side, this data is stored in the form of a binary tree, and each node in this tree is called as a bucket, and the bucket typically has around 4 data blocks. For simplicity, let's say that for n real blocks, this tree is parameterized to have n leaves. And what you'll realize then is that there are many more blocks in the system than there's real blocks. And in fact, those blocks are called as dummy blocks. Now, the purpose of this underlying probabilistic encryption schema is that a server cannot differentiate between dummy blocks and real blocks. For this protocol, the client also maintains 2 local data structures, the position map and the stash. The position map is a mapping from each block ID to a corresponding leaf label on this ORAM tree. And the stash is just an overflowing buffer for blocks. Typically, all tree-based ORAM schemes have this invariant that a block in the system will always reside in either this local stash or on the path to the leaf label on the server tree. To get a better idea, let's just take a quick look at an illustrative access protocol for an ORAM. To start with, consider a client that requests this block with ID 7. What this client actually does is it fetches the leaf for this block from its position map. Then it instantly samples a new leaf and replaces the leaf label with a new leaf label for this block. It then requests this path for this leaf from the server. The server then fetches the entire path from this ORAM tree and returns this back to this client. Remember that this path is in fact encrypted and integrity verifiable by this client. This client who owns the secret key can in fact decrypt all these blocks in the path, remove the real blocks from it, and push it into the stash. And now this client also in fact can service the request, but right after that, it also has to rebuild this path from the stash. It rebuilds this path from the stash, encrypts it, and sends it back to the server, where the server replaces this new path over the former old path. And that summarizes how an ORAM access works. Now, all of the components, the data structures, and the algorithms that run on the client side are typically what we call as the ORAM controller from ORAM literature. And in our work, we focus on how can we secure this, or side channel secure this in an SGX setting. So now that we've covered the preliminaries required for this talk, we'll actually get into the details of ZeroTrace's architecture. By default, ZeroTrace considers an active malicious adversary. And so everything on the server stack, with the exception of this processor, is in fact deemed as untrusted. This adversary also obtains the execution trace, which is inclusive of all side channel artifacts, as mentioned in the formalization of an oblivious enclave execution in our full paper. So here's the first attempt at our solution. We move this ORAM controller that we described earlier into the PRM of an SGX-enabled machine. And here it locally interacts with this position map and stash. At first sight, this might look fine. Also, the ORAM tree itself is moved into the DRAM where the server can manage it. So it can be in a DRAM or your hard disk. But at first time, this attempt might look fine, but in fact, it has several pitfalls. To start with, this controller code that sits on this trusted PRM space is in fact susceptible to all side channel leakages of Intel SGX. The access patterns induced by the ORAM controller on these local data structures too are in fact a big side channel leak. Another concern here is that the position map itself for large data sets could exceed the PRM limit that we spoke of. And finally, enclaves also do not have I/O support, and so it can't really access these it can't access the server tree, which is on the other side. So let's start with solving these problems. And in fact, the fact that enclaves do not have I/O support can be easily fixed by adding untrusted shim layers that can interact with the server on behalf of this enclave. So we get rid of that problem. And the other functionality problem of exceeding PRM limit, well, fortunately for us, ORAM literature has looked at this problem as well, of how can we maintain a small, tiny client state. And the solution from there is to, in fact, recurse. In the basic gist of recursion is, given a data ORAM tree with n leaves at the right end of this figure, you compress this position map with n blocks into an ORAM tree of n by c leaves. And this new ORAM tree is called as the position map ORAM tree. And you repeat this process till this position map is, in fact, small enough to fit on your local client state memory. I just like to point out here that this also implies making an oblivious access to this implies you have to make multiple ORAM accesses into each of these local position maps till you hit the actual for the ORAM data tree. So that removes the PRM problem as well. And in fact, here's an experimental evaluation for the benefits of recursion in practice. Here on the x-axis, we have the number of blocks, and on the y-axis, the time per query. So the recursion does not just relieve the PRM pressure, but in fact, what you'll see is that the timing or the latency per request is also decreasing with recursion. And this is attributed to the fact that in order to maintain side channel security in a non-recursive setting, you have to linear scan these large position maps, whereas in the recursive setting, that's simplified. Now let's get back to the problem of these real security issues that this construction had. So the side channel leakages and the access pattern leakages we need to address. For this, we actually make use of two building blocks, the first one being oblivious functions at an assembly level. So we developed and used a library of oblivious functions. These oblivious functions of ours are in effect wrapper functions over the x86 cmove instruction, which enables oblivious operations in a trusted processor setting. So you can consider this templated OUpdate or oblivious update function, which takes a conditional bit, a source and destination buffer, and the size of these buffers. In short, what actually happens under the hood of this templated function is it brings in into the processor these buffers at the word size granularity of this processor. It then performs cmove instructions or oblivious updates on these registers itself. And finally, it flushes it out from this trusted register space into the untrusted memory space. So the heavy lifting, in fact, takes place within the trusted register space. The other building block that we use is constant time code designs. So since data-dependent control flow branches have led to side channel leakages, we ensure that there are no data-dependent control flow branches in our code. Access into the stash and position map, the local data structures, are also made through linear scans. While this may sound expensive, it's in fact tiny because of recursion. Now we can finally discuss how we envision using ZeroTrace and what it can actually give you. So ZeroTrace is the first oblivious memory controller that runs on a real secure hardware platform. You can use flexible storage backends, and it's also secure against all software side channel attacks since it realizes the oblivious enclave execution definition. ZeroTrace has two envisioned usage models. The first one as a memory protection for secure computation. So going back to the problem that we started with, imagine you have this program P that you wish to compute securely via SGX. P can now be initialized in an enclave that's dynamically linked to the ZeroTrace library. This computation enclave can then use ZeroTrace as the memory controller for all its sensitive data, and thus making data accesses side channel secure in this setting. And here's an evaluation for ZeroTrace in such settings with small data sizes. Here we consider a data block size of 8 bytes, and with 10 to the power 7 such blocks, you'd see that we can make oblivious reads and writes at 1.2 milliseconds with the highest level of security. The other envisioned usage model is as the traditional remote oblivious data storage systems. And here, in contrast with traditional ORAM schemes, where the client has to perform multiple round trips and local computations for a single ORAM access, ZeroTrace instead can allow the client to do simple request-response protocols with this SGX-enabled server. What this gives you is an order of magnitude network bandwidth savings because you no longer have to make multiple round trips for recursive ORAMs. And due to the savings in network bandwidth, what you also get is an order of magnitude access latency decrease as well. And here's an evaluation for ZeroTrace with such increasing dataset sizes. So here on this x-axis, you can see the data size increasing all the way from 8 bytes to a kilobyte, and the time on the y-axis. And what you'll notice is that even with large block sizes of 1 kilobyte, ZeroTrace can actually make oblivious reads and writes at 3.3 milliseconds. And this scales pretty well, even if it's going further down the path, because we use an underlying circuit ORAM. We attribute why this happens in our full paper. And ZeroTrace can even automatically make this decision for you on the fly based off of the number of blocks and the data size that you want to use. Now finally, I'd just like to address how easy it is to use oblivious memory primitives via ZeroTrace. Once your program P is in fact linked with ZeroTrace, wherever necessary within this program, the developer simply has to make use of the two APIs that we offer, ZeroTrace_new and ZeroTrace_access, for creating new instances of ORAMs, as well as for accessing respectively. And with that, I've come to the end of my talk, and I've hopefully shown the design and evaluation of ZeroTrace and showed how it can be used for secure remote computations. And you can, in fact, go and play with ZeroTrace in our GitHub repo. And now I'll leave you with a picture of my favorite Oblivious RAM, and I'll take questions now.
Okay. Use that enough.
You want me to go first?
Yep. Go ahead, please.
Oh, okay. Hi, I'm Adam Aviv from the U.S. Naval Academy. So this is really cool. I do ORAM work, but I tend to be scared of SGX. So one of the things that was interesting that you said, and I thought maybe you can elaborate a little bit more, is the recursion of the position map. So this tends to be the bane of every ORAM design. It's like, how do we deal with the...
Sorry, what's that? Could you repeat the last bit you said?
The position map tends to suck, right? Because
right.
It adds like sometimes a log cubed, or how many recursion steps that you have going down. And this could also increase round trip times. But you said something at the end that I didn't quite understand, where you're saying like you're able to get rid of the round trip times in this model.
Right.
And I don't quite see how that would be.
Gotcha.
Even within all the primitives that you set
Gotcha.
up.
So I guess what I didn't clarify was you in fact do have to do multiple round trips, but it's not on the network stack. It's purely on the chip to memory stack. And this is in fact much more better than having to go across the network stack from a remote client to the server, right? So we do that heavy lifting, but it's on the localized server side. And so you don't have to see the network latencies at all.
Yeah, but just to be clear, like even with like high amount of memory that you have to store within the ORAM, you're still going to have that extra recursion costs, right? So you can't really get rid of that, I'm assuming.
Oh yeah,
all right.
You have that. In fact, recursion is partly most of that cost. Even though it's like 3 milliseconds and 1 milliseconds, most of it is through recursion itself, no doubt.
I have a question.
Yep.
Well, first of all, very nice talk.
Thank you.
I do wonder what is the, you mentioned two building blocks of defeating side channels.
Right.
One is the C move, and the other is the constant time indentation. And what is connection between your building block and actually defeating all types of side channels?
Right.
I think this is this claim is a little bit bold. Can you tell us a little bit more about how you use these building blocks to build a side channel resistant implementation or RAM implementation?
So the side channel attacks in literature are typically against the cache or the data accesses that the SGX makes in the PRM space or outside of PRM space. When we do this, irrespective of whether your data elements lie in the cache or in the DRAM, which is the main source of the leakage in typical side channel attacks, it doesn't matter, because when you have ZeroTrace running, all of these, irrespective of whether it resides in the cache or DRAM, has to be brought in one by one into this trusted processor space, right? And we do all of our heavy lifting within the register spaces. That's exactly why our oblivious functions are all in assembly code. So it doesn't matter whether there's a cache discrepancy in terms of accesses or memory, like there's a difference in memory access from it being responded from the cache or the memory. In fact, both of it still has to hit the register spot before it goes out.
Well, okay, I think, yeah, I'll leave time for other questions.
Oh yeah, sure.
We can talk off.
Sure, we can definitely talk offline.
Hi, Sadek Riazi from UC San Diego. Great talk, by the way.
Thank you.
My question is it read-only or you can also write in the ORM?
You can write as well. In ORAMs, from literature, ORAM doesn't distinguish between read and write. So the adversary cannot even realize whether you read or you wrote your memory.
So to initialize the ORM, you need to access it and then write it your own data?
Yes. So typically, there are multiple ways for initialization, but if you just want a clean state, you can just have the server allocate the memory and not write anything, and then you can start doing incremental accesses and then build it up.
Okay, and another question is, does it support the dynamic size of the ORM?
Right, so the constructions that we use currently do not, but we're thinking about what we can do about that. There are other ORM constructions that can in fact scale, like the hierarchical branch can in fact scale with increasing as well, but not the tree-based ones typically. But
okay.
that's a good question, thank you.
Yue Chang from Baidu USA X Lab. So nice talk.
Thank you.
My question is related to you using the same move to hide the if-else branch, right? But how do you handle the loops, the for loops, something like that?
Right. The for loops?
Yes, something the loops.
Right. So our for loops are in fact always constant time, right? Because it's all based on global parameters. Like the for loops will always be the depth of the recursion or things like that, but nothing that's hidden data or secretive.
Okay, the argument is the control is not related to the private information, right?
I'm sorry?
So can you clarify again? So how do you handle the loops?
What about the loops in specific, though?
Because the loops also related to some private data, right?
No, that's exactly what I meant by our constant time code designs. Our loops are not based off of any private data. The loops are, in fact, just because of how ORAMs work, none of the for loops in ORAMs are actually based on private data. The only possible for loop that could have worked on some sort of secret element is the size of the stash, right? But in fact, we declare a constant stash. So even if they're dummy blocks, the ORAM controller is always sequentially scanning the entire stash. I think that's what you're getting at.
Okay,
Thank you. Oh, yeah.
Just one more question.
All right, sure.
I was actually reminded one of the people asked about. I think they meant write-only ORAMs, not read-only.
Sorry, what's that?
I thought they meant write-only ORAMs. So the other SGS work I've seen using ORAMs that have been really effective have been in the write-only realm. So only the writes are protected and reads are free, because this idea that the transition between the protected state to the black, it really only needs to happen at the write stage, because all the reads can occur locally within the SGX module and don't actually need the same protections. That was kind of the idea that they have. So the write-only space is a lot better. So I was wondering, did you do any comparisons to write-only ORAM in terms of for different workloads and seeing whether or not that's a reasonable comparison for your work?
Okay, so I haven't done that, but I'd just like to say that ORAM by definition does not discriminate between reads and writes. So if you go into this mode where you're discriminating between writes and reads, you're already not really oblivious. You are leaking whether it's a write or read.
Let me be very clear. There are two varieties of ORAMs. There's the access ORAMs, which do what you said, and there's also ORAMs that only protect write access.
Right. Yeah, we didn't do that. Okay. So I don't have a sense for how that will pan out.
Okay, thanks.
Thank you.
Let's thank the speaker again. And thank you everyone for coming to the session. This is break time. Thank you.